The last big topic in chapter 3 is really honing in on this idea of curve analysis, which we've kind of been building up to since we first started talking about the first derivative and increasing and decreasing. So this kind of puts it all together. This is really giving you a nice chart to help you, depending on what you're looking at, determine the features of the other graphs. So what I mean by that is being able to compare an original function with a derivative function with a second derivative function. So this is something, and I have it on the handout sheet that I gave you as well, that is just a nice thing to use as a reference so that depending on what you're looking at, you can figure out what's going on with the rest of the functions. And it can be so hard sometimes when you're looking at pictures to keep everything straight. So this helps organize it. So here's what we've got. I really focus a lot of my attention on this middle column because this is what's going to be asked the most, is they are going to give you the derivative graph. So the number one thing that will be given, not saying they're all like this, but the number one thing, you'll be given a first derivative graph. From your first derivative graph, you can tell a whole lot about what's going on with the original function. So the top parts are things that we did at the beginning of the chapter. If my derivative is positive, meaning it's located above the x-axis, then that tells me that my original function has to be increasing because it has a positive derivative. If my derivative is negative, which means it's located under the x-axis, that means my original function is increasing. Now, those places where my graph of my derivative crosses between the lower and upper half or vice versa, those intercepts are going to be your extrema on your original graphs. So if we can look at these x-intercepts, we are able to say where the original function has extremas. Now, keep in mind, we can only say the x values. We have no way of knowing the y values since we don't actually have an equation for my original function. Now we can take it a step further and look at when my derivative is increasing versus decreasing, meaning a positive slope or a negative slope. If my derivative is increasing, that means my original function has to be concave up. If it's decreasing, my original function has to be concave down, because basically you're looking at the slope of the slope, which is representing your second derivative. If my derivative has an extrema, meaning it has a maximum or a minimum, then that means my original function would have a point of inflection there. Again, x equals only, we have no way of knowing the y value. We can go a step further and do a little bit with the second derivative graph, which we've talked about a little bit. When my second derivative is above the x-axis, it's positive, which means my first derivative is increasing, which means my original function has a concave up interval. When my second derivative is negative below the x-axis, it means my first derivative is decreasing because my original function is concave down. And then where my second derivative graph crosses the x-axis, goes from above to below or vice versa, we would have extrema on the first derivative and points of inflection on the original. So we can really go from one to the other and we can do a lot of comparisons. Biggest thing when you're doing these, make sure you realize what you're actually looking at. It's very subtle, but you want to see, is it an F prime or an F double prime, so that you're answering the questions correctly. So I just want to show you some different examples of things that you could see. So here's an example of a derivative graph, and here are the things that we could know about the original. So I'm just going to do this one as a list, and then I'm going to get into some that are much shorter and don't want everything. So if you are given a first derivative graph, you can actually find 6 different things about the original function. No AP question is going to ask you to find all 6, but they kind of pick and choose which ones they want you to do. So first, if you're looking for when the original is increasing, you're looking for when the graph of the derivative is above the x-axis. So this happens from 3 until we get to 8. This is a delta math question, so it's going from -9 to 9, open interval. So decreasing would be everything else. So decreasing would be -9 all the way till we get to 3, and then from 8 to 9. Now, I know a lot of people have asked, like, what happens when it actually just touches it? Do I need to stop there? I understand that that's a place where the derivative equals 0, but the AP does not require you to stop there. In fact, they actually say you can go all the way through, which I know seems a little bit weird. So extrema are going to be the places where my derivative is going to switch signs. That's going to happen at 3 and at 8. And I can always say what type of extrema it is. So at 3, prior to 3, it had a negative derivative. So it was decreasing after it was increasing. So that is a minimum. And then from 8, before 8, it was increasing and then it was decreasing. So that creates a maximum. I can't tell the y values because I do not have an original function. Concave up. So here's the new piece. Concave up original is going to be when the derivative is increasing. So as it's going on its way up, which is going to happen a couple places here. It's going to happen from -9 until it gets to -4. And then it's going to happen again from 0 until it gets to 5. So it's going to be from here to here, and then from here to here. So concave down is going to be when it's decreasing. So that is going to be from -4 to 0, and then again from 5 to 9. Now your points of inflection, you could either just look at the intervals you wrote and see any time it switches concavity, or visually on your derivative graph, it's going to be any extrema of that derivative graph, and that happens at -4, it happens at 0, and it happens at 5. So that's how we can take a derivative graph and answer a whole bunch of things about your original function. Here's another one. We'll go through the same idea here. So we're going to look at all of these things. I have no idea why I write diagonally. Increasing, decreasing extrema, concave up, concave down, POI. I'll try to color code this one a little bit better. So increasing is going to be when it is positive. Decreasing is going to be when it is negative. Well, this one is hardly ever positive for the derivative, only at the very, very beginning, which is -9 to -8. And then the rest of the time, it stops at 9, it is decreasing. So that means it only has an extrema at -8 because this is a place where the derivative goes from positive to negative. So that is a maximum. So your concavity, so now we're looking at when does this graph decrease or increase. So concave up is when it increases. So it's going to increase not very much, just right here. It's going to decrease all this time and then all of this time. So my concave up intervals are there's only one. Looks like -1 until 4. And then my concave down would be -9 to -1 and 4 to infinity. Or not, sorry, 9 infinity. I'm so programmed to write infinity to 9. So my points of inflection are going to be the extrema on the derivative graph, which is going to be here and here, which is -1 and +4. There are not different types of extrema, so different types of points of inflection. So unlike extrema, where you actually have to label minimum, maximum, point of inflection, you are only expected to list the x values. They put some extra dots here. They're just telling you the points of inflection of the first derivative. That's actually not going to come into play here. I mean, kind of gives you a little bit of information, but not much. So here's an example of one where they don't want everything. I was pulling these from Delta Math as well. So this is one where they give you the derivative graph, which is their most common given information, and they only want to know one thing. And the thing they ask can change. So this one, they want to know when the second derivative is bigger than 0, which means when is the original function concave up? Well, that's going to happen anytime this derivative graph is increasing. So that's going to happen. Again, I like using different colors here. For all of this and for all of this, we're looking for that positive slope so that the slope of the derivative would be the second derivative would be positive. So that's going to happen from -9 until looks like -3. And then it's going to happen again from 3 to 7. So that's one of the ways they could ask just a single question, not the whole list that we've been doing. Here's one, another first derivative graph, where they want to know when would the function have an inflection point. So looking for those POIs. So that's going to be anywhere where the derivative graph has an extrema, because we want the derivative to have a 0 slope, because that'd be the derivative of the derivative. So that's going to happen here. It's going to happen here. It's going to happen here. Now you might be wondering, what about these places? What about here where it looks like it has a 0 slope? And what about, oops, sorry about that. What about here where it looks like it has 0 slope? Well, in order to change concavity, we would actually have to change how the slope is going. So prior to here, we're going positive slope, then a negative slope. So we would have a sign change, which would create a point of inflection. That doesn't happen here because we're increasing and we keep increasing. So my points of inflection, and again, they are just x values, look like it happens at -1, at 3, and at 5. So from that, we are looking for those extrema that are places that we do get that sign change of the slope of what is we are looking at. This one is a derivative graph and it wants to concave up again. So again, concave up means the slope of the slope. So the slope of the derivative is positive. So I'm looking for increasing intervals. I can even use a highlighter here if this helps. So that is here and here. So that would be -4 to -2 and 2 to 5. Sometimes even just color coding things really helps. So this is a second derivative graph. I want to show you one of these. With the second derivative graph, you're kind of limited in what you can do. So with your second derivative graph, primarily you're going to be just asked things about the first original function with concavity and POIs. So if you're looking at a first derivative graph, when it's above the x-axis, or second derivative graph, when it's above the x-axis, it's positive. When it's below the x-axis, it's negative. So therefore, my original function would be concave up from -8 to -4 because that's when it's above the x-axis. And then again from 1 to 7. It is below the x-axis, meaning having a negative second derivative from -9 to -8, from -4 to 1, and then from 7 to 9, so lots of intervals below. And that means your points of inflection are going to be any place that we cross over and have a sign change of the second derivative, which happens all sorts of times. It happens at -8, it happens at -4, it happens at 1, and it happens at 7. So again, we have a lot of options here. Here's the last one I want to look at. So this one is kind of doing a similar thing, but this time it's looking at just one point, one x value, and doing a comparison of everything we know there, kind of doing like a sign comparison. We've done these before. So it wants to know at 5, this is an original function. What do we know about the original, the first derivative, and the second derivative? And I often kind of note these with, is it positive, is it negative, is it 0? So at 5, so x equals 5 is right here. I know that my original function is positive. Looks like it's not very positive. It's like a little less than 1. I know that my derivative, because it is decreasing, my derivative must be negative. And because of its concavity, they put these little green dots to show when concavity changes. Its concavity is upwards. My second derivative must be positive. So what do we got here? We have the smallest one is definitely this one. At 5, it's positive, but it's a very small positive. So this one would come next. And then my second derivative is definitely concave up. So this one will be last. So it gives you a chance to kind of do some checking of things. It also tells you points of inflection values. So it gives you an idea of what we are looking at with these. And that's a whole lot of curve analysis in one video.